I hope all of you have already have the slide, chapter 1, the per unit quantities. So you can view the slide.
Yes. Yes.
Okay. Okay, good. Okay, as an introduction, so it is clear that a detailed representation of each of the three phases in the system is complicated and can also obscure information about the system. So actually, a complete diagram of the power system network representing all the three phase becomes complicated. And no, what you call it, the information can convey as it's intended to convey. So balanced three-phase system is solved as a single-phase circuit made of one line and the neutral return, thus a simpler representation. So meaning that the balanced three-phase system can be solved on a per-phase basis, which is much simpler. And further simplification can be done by removing the neutral. So why the neutral can be removed in the case of a balanced three-phase system? Any reason why? Because the sum up of all three current, the line current will become zero. So that's why you can remove the neutral line or neutral conductor. So it is practical to represent the power system network by a single line diagram, by a symbol for each component. Okay, this simplified diagram is known as a single line diagram or one line diagram. Okay, the one line diagram will summarize the relevant information about the system for a particular problem study. So in the single line diagram, it shows the main connection, and the arrangement of the component, along with the data, such as the output rating, the output rating. Okay. The voltage, the output rating, the voltage, the impedance, the resistance. In case of a transmission line, for example, the conductor size and the spacing are given. And it is not necessary to show all the components of the system on a single line diagram. For example, the relays and the circuit breaker need not to be shown in the load flow study or in the steady state study, but the circuit breaker are must for protection study lah. Okay, in a single line diagram or one line diagram, So the system component are usually drawn in the form of their symbol. So each component, for example, the synchronous machine or generator has their own symbol. The transformer has their own symbol. The transmission line has their own symbol. Therefore, the IEC, the ANSI, and the IEEE, so all these are the international standard. The international body have published a set of the symbol, standard symbol for electrical diagram, which will be used in the online online diagram. Sorry, one line diagram. Okay, these are the main components of a one line diagram or single line diagram. It consists of the bus, the buses, the branch, the lines, the interconnection, the loads. Usually use passive load, which is not involved rotating machines. The passive load, the machine, the synchronous machine, the two winding transformer, the shunt element, the rector and the capacitor bank. So these are all the components usually used in the one line diagram. And this is the example of the one line diagram. Okay, we have what you call it? This is a transformer, two winding transformer with different symbol. And the generator symbol, and the rectangular block is for circuit breaker. Circuit breaker. So this is the delta star connection of the generators and transformer connection. The neutral earthing also can be shown in the one line diagram. Okay, this is the example of the single line diagram of the typical power system. You can see here. So this is the synchronous machine, the synchronous machine with the neutral earthing through the impedance for G1, G2. So this is the circuit breaker, the rectangular block. Is a symbol for the circuit breaker. This is for transformer, T1, transformer. For transformer, both are star connection with solidly earthing, solidly earthing or solidly grounded. And this is the transmission line, and this is the transformer T2 with star solidly grounded on the primary and delta on the secondary. This is the bus bar. It's a bus bar both at the sending and the receiving end that connect all the components. And this is the circuit breaker, the G3, the synchronous generator. And this is the neutral earthing of the G3 with the impedance through the impedance. Okay. So any questions so far?
No, Doctor.
Okay.
Yes.
Okay, this is the example of the 30 IEEE 30 bus system, the one line diagram or the single line diagram. You can see the IEEE 30 bus system. If all the three-phase quantities are presented in this one line diagram, you can imagine how it looks, right? Okay, we have discussed about the single line diagram or one line diagram. Next, further simplification from the one line diagram. with the symbol, for the various components. Now we can draw only the impedance. That's why it's called impedance diagram. So the impedance diagram, in impedance diagram, each component is represented by its equivalent circuit. For example, the synchronous machines or screen generator is represented by a voltage source in series with the effective resistance and the inductance. For transmission line, for example, so we have a nominal pi equivalent circuit for the transmission line, which is usually used in the reactance or in the impedance diagram. The transformer, we have equivalent circuit of the transformer. So means that in this impedance diagram, so each component is represented by its equivalent circuit. Okay, you can see here, this is the one line diagram of the typical power system, which consists of symbol for each component. 1, 2, 3 is for the generator. So this one is load, the passive load, load A, load B. It's a bus bar, and this is the symbol for the transformer. T1, the primary and secondary connection, star connection, solidly grounded. I have to admit someone joined this meeting. Okay. Okay, this is the symbol for the transformer. Both star connection, solidly grounded, neutral, earthing, solidly grounded. And this is the symbol for the circuit breaker, the rectangular block. This is a transmission line, here, transmission line in the middle. Okay, at the receiving end, we have another one, transformer T2, with the star delta connection, star and delta, solidly grounded. And then we have another bus bar at the receiving end, which connect all these components. The synchronous generator 3, the generator 3, it is star connection and neutral earthing through the impedance. You can see here impedance. And this is another load, load B, the passive load B, which is to this bus. So this is the single line diagram. This is the single line diagram. So any question regarding the single line diagram before we transform to the impedance diagram? Okay. Below is the impedance diagram of the one line diagram above. You can see here each component or each symbol is represented by its equivalent circuit. You can see the generator 1 is represented by the voltage source in series with the, what is here? You can see the generator is represented by the voltage source in series with the resistors and the inductance. This is for the generator 2. And this is the bus bar. Bus bar here. So the reference. Normally the reference is at the lowest part. This is the reference bus bar. And this is the what? What is this equivalent circuit? So this is the transformer equivalent circuit, right? T1. You can see here the magnetic circuit. The magnetic circuit of the transformer. The the primary parameters, this is secondary parameters, and this is the magnetic circuit of the transformer at the middle. So the transformer is presented by its equivalent circuit. Now we have a transmission line. So this is a transmission line is represented by a nominal pi equivalent circuit. Nominal pi equivalent circuit, the transmission line. And again, this is the transformer T2. Is represented by its equivalent circuit. This is the primary quantities. This is the magnetic circuit, magnetizing circuit, and this is the secondary quantities. And what's this? This is the load B, the passive element. So consists of the resistor in series with the inductance. And we have the last one is the synchronous generator. This is the G3, represented by the voltage source in series with the resistance and the inductance. So the below is known as the impedance diagram, the simplification of the one line diagram by representing the symbol for each component into its equivalent circuit. Okay, any question regarding this the one line diagram and the impedance diagram? So you can see, yeah?
No, don't have question.
All right.
Doctor, I have question.
Yeah.
Why the two winding transformer have two symbol?
Why?
Two winding transformer have two symbol.
Two symbol.
Two different symbol, but
Okay, you can see here the two different symbol, right?
yes.
This one is the American standard, the coil. This is the American standard.
So,
And this one for British standard.
so both are acceptable lah.
Yeah.
Both are acceptable.
Yeah, both are acceptable.
Okay.
So you can use this circle symbol or this two winding symbol or coil symbol, right? So you can choose either one. Which one is convenient? You see, this is the symbol from the ANSI and the IEEE. From the American and the IEEE standard. Or body lah, standard body.
Okay. Thank you, Doctor.
All right. So any question? Before we proceed with the reactance diagram. So we have discussed the single line diagram, which represented by the symbol for each component. And then we discussed the impedance diagram. Okay, this impedance diagram is also called the positive sequence impedance. Why positive sequence impedance? Because it reflects to the balanced system. We have positive sequence impedance, negative sequence impedance, and zero sequence impedance. So we will study this sequence impedance in the fourth study later on. So for balanced system, we are considered the balanced system. That's why there is no neutral earthing appear in this impedance diagram. And also this is known as the positive sequence impedance diagram. Okay. The impedance diagram can be simplified. Can be further simplified by making a certain assumption and reduce to the simplified reactance diagram. Okay. This is known as reactance diagram. The simplification of the impedance diagram. So what are the assumptions? So this reactance diagram is drawn by neglecting or by removing all these quantities. So for example, all static load. You can see here, there's no more static load, or load A and load B in the reactance diagram. You compare the reactance diagram with the impedance diagram. There is no more resistance. There is no more resistance. You can see here, there is no effective resistance of the generator. So there is no more resistance of the transformer. So there is no more resistance of the transmission line. So by removing this all static load and the passive load, all the resistance includes the generator resistance, the transformer and the transmission resistance, and also the magnetizing circuit of each transformer. You can see there is no magnetizing circuit of the transformer here. There is no this magnetizing circuit, and also there is no shunt or capacitance of the transmission line. So by removing all these quantities, we obtain the reactance diagram or JX. So JX, so reactance only, right? There is no real part of the impedance. So any question regarding the reactance diagram? So make sure you understand what is the one-line diagram or single-line diagram, the impedance diagram, and the reactance diagram. Any questions so far before we move to per unit quantities? Is it too fast?
No, okay.
Okay.
It's okay, sir.
Okay. Okay, in power system, the large amount of power being transmitted in the range of kilowatt to megawatt at different voltage level. So we know that the quantities involved in the power system are kilovolt ampere or megavolt ampere or kilowatt megawatt, the voltage, the current, the impedance of the equivalent circuit of various system components. So these equivalent circuits are interconnecting, interconnecting by the interconnection or by transformer at different voltage level. Okay, as a result, in the analysis, it is useful. So it's beneficial to scale or to normalize the quantities with large physical values. And this is commonly known as a per unit system. So the per unit system actually the scaling mechanism is a method that provide the comparison in power system analysis. Okay, the per unit system is widely used in the power system industry to express values of voltage, current, power, and impedance of the various components, as I said. Okay, it is mainly used for transformer and the AC machine. So for transformer, we have primary and the secondary. So it's useful to use this per unit system. Why? Because the per unit impedance for the transformer is similar for primary and the secondary. Okay, per unit calculation, all base values are only magnitude. What is base value? Is a reference value. It's a reference value. It's a base value. So there are no involved with any angle. It's only magnitude of the phasor. Only magnitude. Remember, there is no involved complex. However, the per unit values are phasor. Phasor form. So you have to consider the magnitude and the angle. Unless the angle is zero lah. So the phase angle of the current and voltage and the power factor of the circuit are not affected by the conversion to the per unit values. So for a common form, so the per unit value is defined as actual value of any quantity in any unit divided by base value or reference value in the same unit. So for example, voltage, right? Voltage in volt, if you divide by the base value of volt, you're going to divide by the base value of ampere, right? So this is the actual value of any quantity, the voltage, the current, the impedance, the kVA, power. So any quantity in any unit divide by the base value or reference value in the same unit. So this is the important definition of the per unit value. Actual divided by base. Nilai sebenar bagi dengan nilai dasar. Actual divided by base. Okay, the per unit values can also be represented as X1 equal to 10%, meaning that X1 equal to 0.1 pu. It can also express in percentage or in ohm. In ohm. For example, S1 equal to 0.1 per unit in ohm. Okay, base value. So what is base value? Or reference value. So by specifying the base value of the current and voltage, the base impedance, the kVA can be determined. So the quantities and base value selected. For example, the voltage. So the base value for the voltage in kV lah, the reference voltage. And current. So the base value in ampere. Current. So for a common representation, the two base value are chosen, which is the base power, the nominal power of the equipment, and the base voltage, the nominal voltage of the equipment. So by having or by knowing these two base value, so we can determine the base current and the base impedance from the from the basic law lah, or natural law of the electrical circuit. Any questions so far? Yeah. Any questions so far regarding the per unit quantities? Okay. Usually the nominal apparent power, the apparent power or symbol S for apparent power, and the nominal voltage V are taken as a base value. For the power S base and the voltage V base. So usually for each component, there are rating from the nameplate, rating, which is given by the manufacturer. So all the values are taken as old base value, because we have a new base value, which is used in calculating the new per unit values. When the whole system together are connecting together, so there is one base or new value need to be chosen. For example, new base value for power and voltage. So meaning that, so we have to determine what is the new base voltage for each component. Okay. Okay, the base value for the current I base and the impedance Z base can be determined based on these two values lah. So how to find the base current? By Ohm's law, S base and V base are known. How to find the I?
S over V.
Yeah, V over Z, right? Or S over V, right? Or you can find the Z first, and then you can determine the current, or directly from the S equal to VI terms, as the apparent power S equal to VI, so I equal to S over V lah. So the impedance, how to determine the impedance?
V over S.
Impedance.
V over I.
Can try by your own. So you have S equal to VI, right? So I equal to what? I equal to S over V, right?
Yes.
And also I equal to V over Z.
Square.
Z equal to V squared over S. V squared over S. Can you try? Did you get at Z equal to V squared over S? All of you got this expression?
Got,
Huh?
we got,
Dapat?
yes, we got the
Did you get?
expression, yes.
The impedance is square of the voltage divided by the apparent power. Z equal to V over I, right? So substitute I equal to S over V. Eh? Then you end up with the V squared over S. Okay. Use this. Put here. Okay, for single phase circuit, so the per unit system is given by this important expression. Okay, for P base, P is the real power. It's measured in watt. P base one phase is equal to the Q base one phase. It's also correspond to the S base one phase. For one phase circuit, PQS are similar. The base value. For example, 200 kilowatt. Here is 200 kilowatt. Here is 200 kilo VA, kVA, right? So the I base equal to S over V. It's one phase. So be careful. This is a per phase quantity. So means that the voltage must be in line to neutral or phase voltage. Line to neutral or phase voltage. So the impedance, Z impedance equal to the R, the resistance, the real part, and also equal to the imaginary part, X, equal to V over I lah, the Ohm's law, or V squared over S. This one line to neutral, this one is a one phase, per phase value. So base impedance, ohms, impedance is measured in ohm. So base voltage or kV squared over MVA is one phase. So base power kilowatt one phase to kVA one phase, and base power, for example, megawatt per phase to base MVA per phase. This is per unit value. The V per unit. The actual value divided by the base value. Actual value of any quantity in any units divided by the reference value of the same unit. It's I per unit. S per unit is the Z per unit. And this is the, you might remember, the impedance can be represented as percentage and the ohm, right? Percentage and ohm. So this is the Z in percentage. Per unit times 100%. Percent of the Z. Or in ohm. Any question? So in case of the complex number, for actual quantity that has a complex number, so same as well, and the per unit values is in complex form lah, or in phasor form. This one in phasor form. The actual value divided by the base value. Actual divided by base value. And this one, the Z is expressed in rectangular form. This one for reactive impedance lah, plus Jx, Z to R per unit plus Jx per unit. And this one, I think you should correct this one. This one is not R, this one P, supposed to be P, S equal to real power, not R, plus JQ. So you can please correct the slide. Okay, later on, correct this later on. Okay. Here the per unit, S per unit equal to the actual value divided by base value. Since S in a complex form, so this is the what? The complex power, the V times I conjugate. And this is the voltage in phasor times the current conjugate in phasor. Okay, this is the real power. The real power, the actual divided by base. Since the S base equal to the P base, right? And equal to Q base. P, Q, S are similar in per unit. Divided by S base or equal to the V magnitude, I magnitude times cos theta lah. This is the basic real power equation for one phase system. Magnitude of voltage, magnitude of the current times cos theta, the power factor, right? And sorry, this one for okay. ZPU equal to Z actual by Z base. So what's the actual value? Class, what is the actual value?
2.65.
Yeah, this is the actual value. So how to find the base value? How to find the base value?
V squared over S
Right.
squared.
Right. KV squared divided by
S.
S or MVA lah. In this case, M, right? Mega, right? It's MVA. Mega, 500 times 10 power 6, right? So what is the base? 22 kilo square divided by 500 times 10 power 6. So what do you get? You should bring your calculator during the class. So what is the base value? The base impedance or reference impedance?
0.968.
0.968.
968.
Huh? 0.968.
968.
Ohm, All of you got the same answer for Z base?
Yes.
Yes.
0.968 ohm base value. Then substitute this here, right? So you get actual value 2.65 divided by 0.968. So what is the per unit value?
2.74.
74.
2.74 PU. All of you got the same answer?
Yes.
All,
Yes.
class. Everyone should get the same answer, 2.74 PU.
Yes.
Yes, sir.
Anyone who
Yes,
still
sir.
didn't get? Anyone who still didn't get the per unit value or base impedance? Remember, the per unit value of any quantities equal to the actual value divided by the base value or reference value. Both the numerator and the denominator must have same unit lah. This one ohm, this one also in the denominator also in ohm. That's why you end up with the PU. 2.74 PU. Any question? Please ask. If you don't understand, ask the question. The international student, okay?
Okay, sir.
Yes, doctor.
Did you get?
Yes.
Yes, doctor.
Yes.
That's good. Okay, now we move on the three-phase, three-phase circuit. Okay, in three-phase circuit, per unit system for three-phase circuit have the same per unit values for line-to-line and line-to-neutral quantities. So meaning that the line-to-line and line-to-neutral quantity are similar. So line-to-line is three-phase quantity, right? Line-to-line, VRY, right? Red with respect to Y, yellow, right? And line to neutral is a phase quantity, red, VRN, for example. Red with respect to neutral. So in per unit, this line to line and line to neutral are similar. Okay, since it's a balanced system, it's become a single phase circuit. The magnitude is similar, the phase angle is displaced by 120 degree. Okay, the balanced three-phase circuit can be solved in per unit on a per phase basis by converting the delta load, delta connection load impedance to star or Y connection, equivalent Y impedance. So we can make up the three-phase into a single-phase circuit. So the base value can also be selected on a per phase or three-phase basis. Okay, in the three-phase system, we have this relationship. The V line to line per unit equal to V line to neutral per unit. Similar. Okay, for star connection, the line voltage, line to line voltage equal to root 3. We have factor of root 3 times the V line to neutral. Okay, this is the magnitude of the line voltage. Root 3 times the magnitude of the phase voltage. So by rearranging this, so we get V line to line PU equal to V line to neutral PU. So the per unit value, the actual divided by base value, the actual divided by base value. So we end up with the V base line to line correspond to root 3 times V base line to neutral. Okay. So S3 phase in per unit is similar to the S1 phase in per unit, the apparent power. So in usual condition or in the actual value, the S3 phase is 3 times the S1 phase. This is the actual value. However, in per unit, the value are similar for 3 phase and the single phase. So by arranging this equation, so what we get, the S base 3 phase equal to 3 times S base of 1 phase. So base value or reference value. This is the base value or reference value in volt ampere, kVA or MVA. Okay, in 3 phase, we also have this complex power. So S3 phase equal to 3 times V phasor times I conjugate phasor, VI conjugate, or root 3 times V phasor times I phasor. So in per unit, the S per unit equal to V per unit times I per unit. So by arranging this equation, so this is important, how to find the base current. The S base, the 3 phase value. Usually the one line diagram or single line diagram, all quantities are 3 phase basis, unless it's mentioned in the question. It's a single phase basis. Usually it's a 3 phase. Divide by root 3 times V base line to line quantity. This usual equation. Okay, we also have already determined this impedance equal to square of the voltage divided by base power, S base, right? So make sure if a 3 phase quantity, the V base should be line to line, and this is for 3 phase. Okay, let's try this another exercise. Given base kVA for 3 phase system is 30,000 kVA or 30 MVA, and voltage base line to line, so 120 kV. Find the S base for 1 phase, V per unit, V base line to neutral, V line to neutral. Given actual line to line voltage is 108 kilovolt. So you are given here, try, everyone should try the example 1. You are given the S base for 3 phase. So S base 3 phase. I have to open another window. Okay, S base 30 MVA. Okay, all these are given. So to find S base 1 phase, straightforward, right? 30 MVA divided by 3. So you should get 10 MVA. All of you got the same answer?
Yes.
Right. So V per unit, actual value divided by base value, right? So what is the actual value?
108K.
Actual value, 108, right? Divided by
120.
120, right? So you get 0.
0.9.
0.9 PU. V base line to neutral equal to line to line quantities, right? Divided by square root 3, right? V phase equal to the line to line quantities or line to line voltage divided by root 3. So what do you get? So what is final answer for B base line to neutral?
69.28 K.
69.28 K. All of you got the same answer, eh?
Yes.
Right. And B line to neutral? 108 divided by root 3, right? So what do you get?
62.35 K.
62.35
35.
kV. So any question? It's straightforward, right? Oh, there's an answer here. We can compare. Okay. So this is the base kVA. So base kVA one phase equal to 10,000 kVA or 10 MVA lah, mega. And then base line to neutral 69.2, right? Okay. And then the line to neutral voltage is 62.3, right? So any questions so far?
No.
No, eh? Okay. So this is per unit voltage, eh? 0.9, eh? And per unit power, So let's say the per unit, the three-phase power, the three-phase power is given by 18,000 kilowatt, eh? This one, there's a new addition to this question, right? Let's say the three-phase power is 18,000 kilowatt. So this is the actual value, the actual value. How to find the per unit power? The actual divided by the base. So its base value, P base equal to 30,000 kilowatt, which is similar. P equal to the S equal to Q, right? Divided by 30,000 kilowatt. Or you can use per phase basis. So you divide by 3 lah. So P one phase, so you get 6,000. This one phase, you get 10,000. We end up with the same answer, 0.6. This is a per unit power. So any question? Because before we continue with the change of base, okay, normally the per unit impedance of the various component corresponding to its own rating, based on the nameplate rating lah. So meaning that each apparatus or each equipment has their own rating or nameplate rating. So the impedance of the individual generator and transformer are generally in terms of percent or per unit based on their own rating. Since we choose one common base, kVA, or reference or base kV for the whole system, so the equivalent circuit are interconnecting or linked together. Therefore, it becomes important to determine the per unit impedance of the various component, which correspond to the common chosen base kV and base kVA lah, or MVA. In other words, since all impedance in any part of the system must be expressed on the same impedance base when making computation, so it is necessary to have a means of converting this per unit impedance from one base to another base. So remember, for the whole system, there are only one reference value or base value. Okay, this is how to obtain the new per unit impedance referred to the chosen base value, base kVA or MVA and base voltage. Remember, there must be two quantity, base quantity, right? You have to choose these two quantity, the base for voltage and the base for the power, kVA or MVA. So the actual impedance equal to the per unit impedance new times base lah. Since per unit equal to actual divided by base, right? So the actual equal to the per unit time base value. This is new, VPU new, this one also new lah, V base new or reference value, the new value. Correspond to the ZPU old, this one also base old value lah, times the old value. Then we arrange, we get ZPU new equal to ZPU old times the ZB old divided by ZB new lah. Rearrange this equation. You bring up this down here. So we get ZPU new equal to ZPU old times ZB old divided by ZB new. Okay, from this expression, the base impedance equal to square of the voltage base divided by the S base. So what we get, ZPU new equal to ZPU old. So we substitute to this for old value and for the new value, B squared over S. So we end up with the per unit new impedance equal to all per unit and the old per unit value, which may express in percentage or in ohm, in percentage or in ohm, times the base MVA new, base MVA old, SB new divided by SB old, times the voltage old divided by voltage new base square. So this is very important equation in finding the new per unit value. New per unit value when the reference voltage and MVA are selected for the whole system. Okay, in case of the VB new equal to the VB old, you can see here from the expression, in case of this base value are similar, so you can cancel out. So it becomes ZPU old times SB new divided by SB old. And this part become 1, right? If the both value, the numerator and denominator are similar, it becomes 1. Okay, let's try this example 2. The reactance of the generator represented as X double prime. So X double prime is referred to the subtransient value, subtransient value of the impedance. X prime is a transient value. No prime is the steady state value. So the subtransient, transient, and steady state is important in fault study. Later on, we'll study it later on. Okay, this is the subtransient reactance of the generator, which is 0.25 per unit. So remember, when there is the X, means that you need to include the J. This is the imaginary part, right, of the impedance. You need to include J here. J 0.25. Also, it's not, whether it's not given, you have to include the J here. Based on the generator nameplate rating. See, this is the old value. The nameplate value is the old value. Base value. Old base value. The voltage of the generator is 18 kV. This is the base value or old value. Old base value with 500 MVA. This one also old value from the nameplate of the generator. So this is a S base old, 500 MVA. So this is the V base old. The base for calculation is 20 kV. Now we choose new base. So this is the new base, V base new, which is 20 kV, 100 MVA. This is also new base power. So this is a new base power, S base new, which is 100 MVA. Okay, find the subtransient reactance of the X double prime of the new base. Okay. Did you understand the question? Or any question so far?
Oh, no, doctor.
Oh, So now, so you have X PU all. What's S PU all? 0.25. And then you have VB all, 18 kV. And S base all, 500 MVA. All this from the nameplate. nameplate rating. All values is stated in the nameplate rating of the generator lah. This is the old value. Old. Now by choosing the new base value, which is V base new 20 kV for the whole system, S base new, which is 100 MVA, determine the new per unit value for the generator. So how to find X per unit new for the generator? Based on the quantities given, you can directly apply the equation, right?
Yes.
Z Pu new equal to what? Z Pu old times
SB new.
KV old over KV new square, don't forget square, oh sorry, times
MVA.
MVA new over MVA old. I have to remember this, Z Pu new equal to Z per unit old times KV old over KV new square times MVA new over MVA old. This expression is derived from here, right? It's derived from here, right? So this is the derivation of this expression. Impedance, not current, not current, not voltage, is for impedance. Here, substitute the value. What do you get? Z per unit old, J 0.25 times kV old, 18 kV over kV new, 20 kV square, MVA new, 100 MVA divided by MVA old, 500 MVA. So what you get? What is the new per unit value of the impedance based on the selected base, kV and MVA?
0.0405.
0.0405
05.
PU. Don't forget J, put J here. And don't forget J, since this is the reactance, right? This is the reactance, the X, the reactance, and you put J here. Because it will affect your calculation later on. When you find the current, when you want to find the current, you have to consider all the complex, complex form. So you have to consider the J, and without J. So make sure you consider the complex form, quantity. Since there's only reactance, you put J. J 0.0405 per unit. So this is a new per unit value based on the selected of new base. This is a new base, right? 20 kV and 100 MVA. Any questions so far?
No, doctor.
No. 0.0405 per unit, right? Ladies, okay? I didn't hear any voice from ladies, okay?
Yeah, yeah, okay, Doctor.
All right. Okay. So let's proceed with another example. Maybe this is the last example before we stop, right? Okay. Exercise 2. Exercise 2. Okay. Okay. Find the X as new. Okay. You are given the generator rated at 10 MVA. Okay. This is the old value from the nameplate. V base all equal to 20 kV. So what is kV old? kV new? Same, right?
Yes.
kV old, the numerator, the denominator is kV new, right? Old divided by new, multiply by MVA new, or SB new. What is SB new? 100 divided by SB old. So you get J9, you right. Any question so far?
No.
Clear?
Yes, clear.
No.
So please ask, if you had any question, please ask. Okay. No question on exercise 2? Okay. Next exercise. Okay, this one I put in the forum, forum in e-learning. Have you checked it? I put in forum in e-learning.
Not yet.
So you can respond to this forum in e-learning. I will see in the next class. I'm going to solve this example problem or exercise 3. Any questions so far? Or you can try now. Try to open the forum in the e-learning. Any questions so far?
No, sir.
So please ask question if you have any unclear things.
Sure, doctor. So we have to solve that question and upload the answer on the e-learning.
Yes.
Yeah. Okay.
There's a class activities Otherwise, it's difficult to make an activity.
Yeah.
It's not like face to face, right?
Exactly.
I can ask you to come in front and do the exercise.
Sir, I'm still not added at e-learning because
Yeah.
I just registered yesterday.
You can upload anytime.
Okay.
Anytime. But within this period of chapter lah.
Mm-hmm.
So I open to any question. You can ask me. Can we still have time? 15 minutes. Is it too fast or what?
Okay je.
Okay.
Okay.
So make sure you know how to draw the impedance diagram. Usually the single line diagram or one line diagram is given. So make sure you know how to redraw the impedance diagram or the reactance diagram. Remember, from the single line diagram, from the component of each element, then we draw the impedance diagram by considering the equivalent circuit of the component, or simple symbol, right? We draw the impedance diagram, and then from this impedance diagram, we can transform it into the reactance diagram by neglecting by the assumption. For example, the magnetizing current is very small in the transformer, so we can ignore the magnetic circuit of the transformer. So we can ignore the value of the resistance, all the effective resistance, because it is too small compared to the leakage or the reactance of the line, for example. So by removing this resistance, the loads, load also we remove in the reactance diagram. The loads, the magnetic circuit, the shunt elements, or the capacitance are removed in this reactance diagram. Then from the reactance diagram, we introduce the per unit quantity. How to find the per unit value for each component in the reactance diagram or in the impedance diagram.
Doctor, I have a question. I have a question for exercise 3. For the VB all, we need to take
Hold on. It's a Saturday, okay?
33 over 11, right?
Yes, 10 MVA, 33 stroke 11 is the nameplate rating of the transformer, the old value.
Equal to 3 kV.
33 kV on the primary side, on the or high voltage side. 11 is on the low voltage side or secondary side.
I think that 33 divide by 11.
33 divided by 11. Yes, correct. 33
Okay.
stroke, no, stroke 11 lah. 33
Right.
is on the HV side, 11 on the primary side.
Okay. Alright, thank you, Doctor.
Alright. This one Z. Z is given in percentage. So impedance 10% is given in percentage. And this is the resistance in 1%, equal to 1%, also in percentage. Or this one equal to 0.1 pu, this one equal to 0.01 pu lah, the old pu. And then based on this new base, the selected base, 200 MVA and 22 kV, which is referred to the primary side of the transformer, or HV side. You see here, 22 is the new base value. What is the old value of the transformer? Is 33, right? So this is the old value, and this is the new value. So you have to choose one, right? We have to choose one common value, one base value for voltage, one base value for the power, for the whole system. You can choose only one common reference for the whole system. So find the Z base. So what is the base value referred to the high voltage side and low voltage side, or primary and the secondary side? What is the base value? And then find the actual value of Z and the resistance, referred to the primary and the secondary. And then find the losses, the transformer losses, due to the winding resistance, right? In actual value, in kilowatt. And the kilowatt is an actual value, right? If 0.033 per unit current, based on the selected base, flow through the resistor. What is the actual power losses in kilowatt? So means that how to find the actual value? The per unit value times the base value. You get the actual value lah, right? Since per unit equal to actual divided by base. Actual equal to per unit times base value. So you have to find what is the base value first lah, the active power loss. Then we can discuss in the next class. And please upload into the forum of the e-learning. Any question?
Yes.
How the class so far? Other class, okay?
Yes, okay.
Okay.
On exercise 3, when you say you choose a common phase,
So don't forget to scan the attendance. So if no question, so we continue on Wednesday, right? Our class, 11 to 12,
All right, Doctor.
Okay. Okay, thank you, class.
Yeah, thank you, Doctor.
Okay, welcome.
Yeah, Doctor.